I had not expected you all to stick around. Well, thank you for doing it. I thought talking to myself. So, clocks. Back to the issue of clocks. Clocks is really the story of a type of oscillator. So oscillation, vibration, they're really the same thing. A rhythmic motion that takes place in a mechanical system spontaneously. Those are all oscillations or vibrations. Oscillation is probably the more general word than vibration because it includes things that aren't mechanical too. But the words don't matter so much. Is that we've got a system that's got a stable equilibrium can spontaneously go through a cyclic motion over and over again. And what's it doing? It's working its way around the stable equilibrium, prevented from settling in the stable equilibrium, really because it's got extra energy. We've seen this since almost the start of the semester. The things that have stable equilibria go through the cyclic motion. As long as they hold on to the extra energy, they just can't stop. They can't be motionless at equilibrium because then they would have no kinetic energy. They would have a minimum of total potential energy. They wouldn't have excess energy. The excess energy just keeps them going. So a ball rolling back and forth in a bowl, a tree swaying back in the wind, swaying back and forth, prodded into motion by the wind. These are just oscillating systems. And the oscillators that are most interesting for the use in clocks are ones known as harmonic oscillators. And the recipe, or the requirement for harmonic oscillators is pretty simple. Stable equilibrium and a restoring force or other restoring influence. It could be a torque too. That's proportional to how far you are from equilibrium. So what I didn't bring out is that big pendulum. But I played with that enough last time to show you that, and do it with a little pendulum. The little pendulum has a stable equilibrium. Here it is. It's pretty much in the stable equilibrium. It has almost no extra energy, and so it's pretty much motionless at the stable equilibrium. If I do work on it, add energy to it, and then let go, I guess for you guys to see, I'll go left to right. It's moving back and forth about the stable equilibrium, unable to stop because of the extra energy. Each time it gets to the stable equilibrium, it's moving, and inertia just keeps it going on through. So actually, these harmonic oscillators have, it's sort of I view it as a battle between two effects. An inertial effect that is trying to keep the major piece of the system moving in a straight line at a steady pace. So that's inertia. And a restoring force, or restoring torque, something pulling back towards the center that is trying to keep settling the thing at center, at the equilibrium. And so inertia, each time it gets to center, inertia keeps it going out the other side. The restoring force draws it back. It comes back through equilibrium, goes out the other side, back and forth. Rather than endlessly talk this over, questions about this. The idea that you've got a stable equilibrium and an inertial part and a restoring force part. We'll see an inertial part, restoring force part every time, over and over again. Yeah. Okay. Is the momentum larger? The momentum is changing back and forth. It's going from rightward momentum to leftward momentum to rightward. So the momentum is not a retained quantity in these stories. Momentum is going all over the place. Energy is retained. So the total energy in it is keeping it moving. This guy, these probably have similar amounts of energy in them right now, give or take. This guy's going faster, as you'll notice. We'll see that it's got a stiffer restoring force. It cares more about how far it is. Is this addressing your question at all? Or the length doesn't matter. The length does matter, but it matters not in the fact that they have this rhythmic motion, but in how long it takes to go through that rhythmic motion. We'll see that when you have one of these harmonic oscillators, so again, it's a category of all possible oscillators include lots of oscillators that do strange things that have rhythms that aren't predictable in various ways, or not easily controlled. These guys have a very well-controlled rhythm, which is the cool part about them. But the time it takes them to go through the cycle depends on the battle between the inertial part and the restoring force part. The more inertia there is, if inertia is sort of dominant, it's going to take a long time for the restoring force to turn around the moving object and bring it back. And therefore, the time it takes to complete a cycle, which is known as the period, is going to be long. And this is an example of a harmonic oscillator with a relatively long period. Why? Because as you pull it away from the center, a restoring force does appear, but it's not very strong. It's kind of wimpy. This guy doesn't care very much where it's located relative to the equilibrium. This guy does. If you take it only an inch or two away from center, its height has changed a lot. It's tilted a lot. It's pushed back pretty fiercely. The shorter, if I made it even shorter, it really would care about how far you took it from center. So you okay with the idea that the restoring force is stiff? I'll show you other examples of this. So the stiffer the restoring force is for a given inertia, these balls are identical other than color, same mass. This got a stiffer restoring force. It's going to go through its motion faster. Tick, 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 tick. This is suitable for a wall clock, the old hang 'em on the wall short case clock. Not very long. It ticks about once a second. This guy, which is about 4 times as long, turns out that 4 is the right number, takes twice as long to go through its period. It's slower. That's more for a grandfather clock. And the giant one that I didn't put up is, we noticed last time, is only like 5 seconds because it's so long. So length matters a lot. In fact, when you set up a clock, and this is the pendulum clock I have in my office. It's just it's a skeleton clock. It's the movement without any case at all. This guy has a pendulum that's about that long. It's in between these 2 lengths, and it's adjustable. Every time I drag it up here, I mess with it, and it doesn't keep good time for a while until I play with it. There's a little adjustment on its pendulum down here that allows a little screw thread that allows me to change its length a little bit and get the timing just right so it keeps good time. And about the time I get it keeping good time, I drag it up here and mess it all up again. Yeah. Is momentum conserved? Clearly momentum is a conserved quantity, but it's not very interesting in this context because the momentum of that pendulum is changing all the time. It's exchanging momentum with its support all the time. I'm going to go grab the big pendulum so I can talk about it. 1 second. I'm coming back. Romeo, Romeo, wherefore art thou? Sometimes you just got to do it yourself. All right. So about momentum. This ball can exchange momentum with the room by pulling on that stud up there that's supporting this. When the ball's over here, it's pulling the stud to your left. When the ball's over here, it's pulling the stud to the right. So it's exchanging momentum with the room frequently. And as a result, the momentum of the ball is changing it's not particularly interesting, okay? The energy, however, is interesting because it can't do work on the stud. The stud never moves. It's unable to get rid of energy. So it's the energy that's trapped in this, not the momentum that's trapped in it. Is everybody okay with that idea? and as a result, it's kept moving by its inability to get rid of that energy. This guy, because it's got a very long support, this pendulum is so long, it's very slow. The ball is almost indifferent to where it is relative to equilibrium. It's almost hard to find the equilibrium. I have to hunt around a little bit to sort of identify it. That's not true for the yellow ball over there, which has got a very short string. It fights significantly when I get it even an inch or two away from equilibrium. So this guy has a weak restoring force. The force shows up. It is proportional to displacement from equilibrium, but it's not very big proportionality. It's you take it a foot or two, you start getting a decent force. Whereas over there with the short pendulum, take it a foot or two, you get a huge force, or you can't even get it a foot or two away. Okay? Yeah. For a pendulum, the biggest thing that impacts the restoring force is the length of the string, and more on that in a second, and the strength of gravity. Suppose we moved over to Jupiter where the strength of gravity is really strong, it's pulling like crazy. The restoring force I would get by coming a little off center would be much stronger. Whereas if we were on the moon where gravity is weak, it would be much weaker. So one observation is the pendulum clocks are based on these devices, keep good time only if you keep them in the same gravity. You take them to the moon, they run differently. I mean, my clock, my pendulum clock, take it to the moon, it would run a little over half speed, a little less than half speed. You'd have to fix it. You have to make the pendulum much shorter to compensate for the fact that you have shifted to the weak gravity. But for practical purposes, this means you have to adjust the clock when you move it. When you settle the clock in your house, pendulum clock, you adjust it to fit the local gravity. Danielle? What is it about a pendulum clock that keeps it going? Yes. Okay. So this is an interesting question because so you can see a pendulum keeps steady pace, and the other thing about it we'll talk about the size of the swing doesn't matter, which is truly important. But there are two other things you need to make a clock, and only two really. You need a device that counts the number of swings. It just literally ticks them off and counts 1, 2, 3, but you don't actually do it in terms of 1, 2, 3. You advance. This clock has a bunch of gears in it that advance. The gear advances a certain angle. The gear closest to the pendulum advances a certain angle every time a swing is completed. And it connects to other gears that advance the hands at the proper rate, so the minute hand makes one full circle per hour, and the hour hand makes one full circle every 12 hours. So all those hands are doing is counting the swings. They're counting them in a funny unit that happens to be seconds and hours and minutes, but it's a counting system and nothing more. Can you follow that idea? That the hands and all that, they're just counting swings. They're adjusted so that they look like time. The other piece that you need to make a clock is a piece that makes up for the energy that is lost inevitably by imperfections in the real world. Air resistance, friction. And what makes up for that, the energy that's lost, is these descending weights. So winding this clock consists of doing work on it, adding energy to it. The simple way, I just pull down on this cable and up goes the weight. So I am doing work. You can see I'm doing work. I'm pulling down and it's moving down. The weight's being lifted and it's pulled up and it's moving up. Work's done on it. I just invested energy in it. And it now has enough energy to run for about a week. That was all it took. It will gradually, as that pendulum swings back and forth, I'm not sure I got a picture of this. I don't have a picture in my notes of what's called the escapement. There is a device attached to the pendulum. Have I stopped the pendulum? I think I did. There's a device attached to the pendulum that has two teeth in it. And the teeth rock back and forth as the pendulum rocks back and forth. And they allow a toothed wheel to advance one tooth every half swing. And why would the wheel want to advance at all? Well, the weight is hanging on it, applying torque to it. That toothed wheel wants to turn because as it turns, the weight descends. And so, so there's a big torque exerted on it by the weight. And as the pendulum goes back and forth, it allows that tooth wheel to advance one step at a time in sync with the swing. And attached to the tooth wheel are the gears and the hands. So that's what's happening is that the gears are advancing at the right pace, limited completely by the pendulum swing, and the weights, the torque, the weight exerts on that tooth wheel not only causes it to turn as the rocking pendulum allows it, but it also gives the rocking pendulum little pushes. Every time the pendulum completes a half swing, you get the little nudge that adds a little energy to it. So it's approximately this effect, that as the pendulum is swinging, there's a release over there, there's a release over here that gives it a little push, and then the same over there, and as it goes over there, a little push again. So it's getting a tiny tap every time the pendulum completes half a swing. And that makes up for any energy that is lost by the pendulum due to imperfections in the real world. Okay? Without that little push, it wouldn't go forever. This pendulum, it's got a lot of mass there, which is good. It's a real compact pendulum bob with a lot of mass in it, but it's pretty broad, and it experiences turbulent airflow. We've done this, right? It's a ball moving through air. It has high pressure in front, low pressure on the sides, and a turbulent wake. That's terrible for a device that wants to keep moving for years. So that thing loses energy pretty quickly. You do better to get a more aerodynamically designed pendulum. And so all realistic pendula for clocks are turned into discs that are cut more like a aerodynamic shape, so they slice through the air nicely, and they leave a very small turbulent wake behind them. And they retain their energy better. It turns out that the better the harmonic oscillator is, the oscillating thing is, at retaining its energy, the more accurately it keeps time, or the more precise its rhythm is. If it loses a lot of energy with every swing, you have to make up for it with a mighty push every swing. And the push inevitably influences the pace at which the swing occurs. If you have to give this guy a shove all the time, you can kind of mess up its rhythm. You know, I'm being goofy here, but you can imagine, I need two people, somebody over there pushing back. We can make it go faster if we want to, right? We can just sort of throw it back and forth between us, and that doesn't count. So the best pendulum, it doesn't tick off time uniformly. The best pendula are ones, or best harmonic oscillators in general, are ones that retain almost all their energy during a cycle, and need only the faintest push to keep them going. So the push has no influence, no significant influence on their timing. All right? There are fundamental reasons why, as it decays, you lose track of exactly what the timing is. But that's beyond what we needed to focus on. About pendula. I told you before, just to step back, harmonic oscillators. Harmonic oscillators have this amazing benefit relative to any other oscillator, that the time it takes for them to go through their cycle, their period doesn't depend on the amplitude of their motion. That's going to be important for clocks because this clock can't control how far that pendulum swings to better than a percent or two or something like that. It just depending on probably the barometric pressure and other things, it's going to be swinging a little differently on one day versus another, the temperature, things that you really can't control. So the fact that a pendulum has a period that's the same whether you swing it a little. I should also say, a pendulum's not quite a perfect harmonic oscillator. It's very close. The restoring force is almost exactly proportional to how far you are from equilibrium, as long as you don't go very far. If you go really far, for example, if we go 20 feet over that way, the ball's going to be way up high, almost parallel to its support. Things are going to get strange. It's not going to have the right restoring force. So you stay down here. So pendulum clocks work in the vicinity of equilibrium, not wildly out to the side. But assuming you do that, and you have what is effectively a very nice harmonic oscillator, the period is the same whether it's this little dinky swing or whether it's a great big swing, sort of as far as you want to use it without beginning to violate that rule I said about don't go too far. Okay? It takes the same time. The reason it takes the same time is just that, yes, you have farther to go when you swing hard, but the restoring forces get stronger with distance, so they make up for it. They perfectly compensate. If you go twice as far, fine. You get twice as big restoring forces. Everything compensates. Questions on that idea? So it's a harmonic oscillator. It is, however, a slightly unusual one. The classic harmonic oscillator, just to remind you what that is, when a physicist thinks of a harmonic oscillator at its simplest, where you have an inertial part and a spring-like restoring force, the simplest example is a mass on a spring. I mean, this is it. This is the classic harmonic oscillator. Gravity seems to be involved in it because it's vertical, but it turns out gravity is just pulls the whole thing down. We saw this with spring scales. It shifts everything down a bit. If I turned off gravity, we would see this. This would be equilibrium. Gravity's presence pulls this down, makes this equilibrium, but otherwise everything's the same. It still bounces about equilibrium, and we can sort of ignore gravity. The story here is the battle between the inertial part, which is just that mass, and the spring-like restoring force, which is the spring. That's it. That's the whole story. And whether you bounce it a little or a lot, the period's the same. There's a big bounce, tick, 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 and here's a little bounce. Not little enough. Little. Tick, tick, tick. Steady rhythm. It has all the features of a harmonic oscillator. Life is simple. And if you want to slow down its period, increase its inertia. How do you do that? Put a bigger mass on. So we take off the little mass. We put a bigger mass on. We drop it. We break it. No, I didn't break it. It shifts down farther because of the gravity problem. But now, tick, tick, tick. It's slower. More inertia. The battle between inertia and the spring-like restoring force. We've given inertia the advantage. I can undo that by going to a little dinky weight. This is probably so dinky it's ridiculous. Dink, 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 right? Now we let the spring-like restoring force win. So life is pretty simple. You play with the mass, and you increase the mass, it goes slower. More inertia. On the other hand, if you strengthen the spring, stiffen the spring, it goes faster. Things are simple. Can you follow that so far? Any question about that idea? So back to the pendulum. It's a little weird because pendulum is one of the few cases where if you add mass to the pendulum, you don't change its period. I'm thinking, how can I add mass to the pendulum? I'm not going to jump on it, sorry. Okay. It's not enough, but here, if I add that guy there, it's still nothing much changed. And why not? Well, the answer is that when I added this extra mass onto the pendulum, and when I added this mass to the pendulum, I increased its inertia, and that by itself would slow things down. But I also increased its weight. And the weight is responsible for the restoring force. It's a gravity-based restoring force that has to do with weight. So this is a weird case where the restoring, as you increase the mass and therefore the inertia of the object that goes through the motion, it's a unique, almost unique case where you also strengthen the restoring force. And because you do that, it compensates. And pendula have this unusual behavior that their period of motion, how long it takes them to go through a cycle, doesn't depend on how much mass there is in the pendulum. A big pendulum, little pendulum of this length will have the same period. And you know this actually when you are the pendulum at a swing set. You go to the park, take your niece or nephew to the park, whatever, and you put them on the swing, and another person's next to them who's significantly more massive or less massive. As long as they're on the same length swing, it takes them the same time to go through the motion. I hope you've noticed this, because regardless, the one who has twice the mass also has twice the weight, and it compensates. So, that said, the period of a pendulum depends only on gravity and the length of the pendulum. Oddly enough, I think I got it in here somewhere. Yeah, it's unexpected, but oh. Must be in here somewhere. Yeah, it is in here. It's right here. The period of a pendulum, and I won't test you on this. I would test you on the direction. I won't test you on this. There's a square root in it, to the 1/2 power. The period of a pendulum depends on the length of the pendulum. The longer, the slower. And it depends also on the strength of gravity. The stronger gravity, the faster the pendulum goes through. It turns out that you take the length of the pendulum, you divide it by the acceleration due to gravity, take the square root of that. That gives you the period. Just give it to you without any proportionality constant. Length. Yeah, it gives you the period directly. Okay? The fact that it goes to the square root, I don't care. I mean, it's cool, but it doesn't matter to you all. You won't remember it. This, however, explains why if you want a pendulum that takes twice as long if you start with this guy and you want a pendulum that takes twice as long to go through its motion, you have to go to 4 times the length, not double, 4. And so the grandfather clock has almost a meter long. If a pendulum that's almost a meter long takes 2 seconds to go through an entire motion. A pendulum that's 8 inches, give or take, I think it's a little less than 8 inches. Doesn't matter. 1 second pendulum. Okay? This guy, because it's somewhere in between, I've never quite figured out. It's a second and it's like 1.2 or 3 seconds. I've never figured it out. I tried counting teeth, and I gave up after a while. Too hard. Any questions? Yeah. The changing weight gets compensated for. So if I clip on some extra mass onto that swinging pendulum bob, it won't change the period. Yes, you'll have more mass, but you end up with more weight that compensates. It doesn't matter. Only the length matters. And length is slightly adjustable, so now you do have a way to control the pendulum's period and fine-tune the clock's ability to keep time. All right? What else? All right. So that's a pendulum clock. It's not very portable. Among other things, tilting it is a disaster, but even worse, it depends on the strength of gravity. So if you move it somewhere where the gravity is stronger or weaker, take it up into the mountains, gravity gets weaker. Take it to the North Pole, gravity gets stronger. So you have to adjust. How do you make a portable clock? Well, to make a portable clock, you shift over to a harmonic oscillator that doesn't depend on gravity. It has a period that's independent. Not only is it a period that's independent of gravity, but isn't even sensitive to gravity. And the classic solution to that problem is a torsional balance. Let me just drag this guy out. It wants to tip over, so I have to weight it with a. Yeah, this is probably as good as I can do. Physicists love lead bricks. That's a lead brick. But if you can you see this on here? Or is it hidden behind? Yeah, it's hidden. Bad planning. Try again. Pull it back. So there's a line on here, which I hope you can see now. And if I twist it away, that's equilibrium. If I rotate it and let go, it oscillates torsionally. It's oscillating about an equilibrium orientation, angular position, if you like. And the period of its motion about that equilibrium orientation doesn't depend on how big the motion is. It's another harmonic oscillator. So here's a mild motion, tick, tick. I guess I can, yeah. It's not worth zooming. Its period of motion doesn't depend on the amplitude of motion. Big motion, little motion, you get a steady beat to it. So that isn't quite the finished form. The finished form for one of these torsional balances or ring balances, you get a couple different versions of the name. It's a little wheel. There's a little wheel with a little axle. How big? Size of your thumbnail. And it has rotational mass, and that's the inertial part that you need for a harmonic oscillator. And it needs a restoring force that's spring-like. So it has a coil spring. So that little coil spring, it's a strange coil spring because it's a spiral. It's not a cylindrical coil spring like I was using over there with a bouncing mass. It's a spiral that gets bigger and then connects to the ring at the outside and connects to a fixed spot on the inside, or vice versa. So this ring now has an equilibrium orientation. When the tiny wheel and its axle are mounted in bearings that are fixed, that wheel can turn, can rotate in its little mount, but it's pulled back always towards its equilibrium orientation or angular position by the coil spring, by the spiral spring. So to show you one of these, this is an antique Carriage clock. And so these were common 150 years ago, give or take. They're a nice portable clock. You wouldn't want to carry it in your pocket unless you've got big pockets, but deep pockets. I will put it up on the front, the side of it. There we go. Okay, so you are looking at the balance ring. Here it is. There's the little ring. The spiral, the spiral spring is so thin you can't see it yet. You have to see it live and realize, oh yeah, it's hair thin. And the axle of this wheel sticks into this bearing. It's a little jewel bearing. I think jewel bearings themselves are kind of fascinating. They take the axle and they polish it to a needle point, basically, and then they have it sit in the middle of a cup-shaped ruby or a gem, a hard gem. Why use a gem? Because it's so hard, it experiences essentially no wear. And you have the little pin sit right in that cup, and as the pin rotates, it experiences frictional forces, but they're so close to the center, to the pivot, to the point about which they're rotating, they exert no torque. Remember that? If you push on the hinges of a door, you produce no torque with your forces. So the forces, the frictional forces that pin experiences are so close to the pivot itself that they produce no torque, no noticeable torque. The point is that basically this little axle rotates almost perfectly freely, and for years, and without any lubrication. And so clocks and watches up until the quartz clock era, they would be listed as 17 joules or 21 joules. The joules were the bearings. These tiny pins sticking into tiny joules, turning almost effortlessly. Anyway, so that's a little ruby here with a pin sticking into it that is the axle for that wheel. There's another one on the bottom. So this guy is currently not rotating. It is at equilibrium, and it has a device also that is watching its rotation and would advance the hands, tick, 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 if it were moving. So I'll get it moving, but to do that I have to wind it. So I am doing rotational work on a spring that's in this, the so-called mainspring, which is an energy storage system, and now provides the same forward force that the weights did on the pendulum clock that want to make the hands move forward. But to get them moving forward, I have to get this balance ring starting to tick. And to do that, I'm just going to shake it rotationally. I just used inertia, rotational inertia, to make that ring fight me and get started moving. You can see it ticking now, I hope. Can you see the ring going? We can zoom in. Not drive us crazy. There we go. Oh, now you can see the coil spring here, the spiral. See that little spiral spring? That is providing a restoring force as this guy's rocking back and forth. It's got a very strange, slow frame rate, so you don't get. It's not like watching. It's like watching YouTube 15 years ago or something. Back when they had slow internet. Anyway, you also can see the tooth wheel advancing over here. So that's being allowed to advance tick, tick, tick by the half periods of that wheel rocking back and forth. What about gravity? Gravity acts at the center of gravity of that wheel, which is right in the middle of the wheel, right in the middle of the axle, where it's being between the two supports. Gravity does almost nothing to this. It exerts no noticeable torque on it, and it exerts a force, but the force is perfectly supported, canceled by the axle bearings. So gravity has no effect on this. It'll operate just fine, right side up, sideways, whatever you like. And this kind of timekeeper based on a rotating ring solved ultimately. Well, it made portable clocks useful, and you can make these very accurate. This one is not super duper accurate, but with better engineering, they ultimately became sort of chronometers. The chronometers well, what's the story? There is a book that is now probably 15, 20 years old, something like that, called Longitude, which is fun to read. So I recommend it as just interesting reading. It is the story of solving a problem that was terribly important to the sort of the mercantile world back in the era of sailing ships. If you wanted to go somewhere from, say, you wanted to sail to India or something like that to pick up spices and come back to Britain, you had to know where you were. You didn't want to go crashing on the rocks here, there, and everywhere. You had to know where you were, and it was easy by looking at the sun and the stars to know where you were in latitude. You could tell how far you were from the equator. What you couldn't tell with any reliability for a very long time was where you were in longitude, that is east and west, because there's no reference, nothing, by looking at the stars in the sky and stuff like that, you can't tell where you are in longitude unless you know exactly what time of day it is and what should be overhead at what location on the rotating Earth. The Earth's rotation messed up your ability to know where longitude, what your longitude was. And so there was a prize offered by the British government, a fantastically huge prize to solve the longitude problem. And it had a specific specification. You had to be able to know where you were within something like 1 mile after a multi-week sea voyage. You had to know east-west, something like a mile, and to avoid crashing on the rocks or something like that. So it was a problem that killed many people. Were lost at sea because of failures to know where they were, east-west. It was solved, finally, by a guy named Harrison, who, on his 4th version of a clock, and the smallest of his clocks, it was only about this big, finally, when he got it going, based on a balance ring like this, it was just beautifully constructed, and everything about it was carefully tailored so that it had the smallest pushes, just everything right, and it was able to meet the criterion. They sailed to the New World and back, and kept the time within. It had to gain or lose no more than 5 seconds in something like a month or 2 sea voyage. He had great trouble getting paid off, as you might expect, 20 years or something like that, for them to finally, the government to finally pay him up. But he solved it, and the story is kind of cool story. All right, balance ring clocks. So these not only would show up in these carriage clocks, but they were the clock of my youth. So the watches that I would wear had these in them, and the pocket watches, all that stuff. What finally killed those off for the most part, except if you want to pay a whole lot of money, you can get a super duper fancy one, Philippe Petit or whatever, these fancy chronometers that almost keep time as well as a $3 watch from Kmart. Sorry. Yeah. Those balance ring clocks. As kids, we would try to figure out how much your watch gained or lost over the course of an hour or so, which was not trivial. My watches usually they'd be off by a good minute every day. So you know you get a watch. Wow, it runs 3 minutes fast every hour, 3 seconds fast every hour. We could predict when the bell would go off. It was always, you had to do something when you're waiting for the bell to ring, right? As you probably are right now. For us, it used to actually be an issue. Like it was difficult to predict. Now you can get it down to the millisecond on your phone. Boring. But these were all. I mean, apart from being fancy jewelry now, you can do much better with a very simple watch. The simple watch. Thank you. The last generation of watches that people actually wear, some of you probably still have them, are these the quartz watches. And they're based on a tiny tuning fork. And I had the tuning forks in here earlier, but the other day, a tuning fork is a harmonic oscillator. It has two masses and a springy structure in between. And they oscillate like this, in and out. The two tines of the fork swing toward each other and away from each other about an equilibrium shape. Despite its complexity, the fact that it's this U-shaped structure, it really has an inertial part and a restoring force part. The restoring force is proportional to displacement. It's a harmonic oscillator. The whole works just fine. So it goes back and forth like this. And the more mass you have on those arms, the slower it goes. The stiffer the arms are, the faster it goes, and so on. Well, the earliest of the tuning fork watches were physical tuning forks. They were little metal ones. There was a watch called the Accutron that showed up in the mid-60s, I guess. And you could hear it whistle, which was kind of cool. And one of my friends in college had one. He is now a member of this department. And he went up after class one day when they had a whomping magnet. This tuning fork was driven magnetically. There's this huge magnet in the front of the class, and he went up and he stuck his watch into that magnet. And it shrieked, and I could hear it from across the room go, and it never worked again. But he had bought it from what was then Abercrombie & Fitch. It's been around a long time. During that era, it was like the Sharper Image. It was one of these fancy buy the super gadgets from companies. And he took it back and said, it broke. And they went, oh, yeah, it's broken. They replaced it for free. He didn't try it again. Anyhow, those were the old tuning fork watches. They were subsequently replaced by quartz ones. So instead of a metal tuning fork that was driven magnetically and therefore was susceptible to being put in a strong magnetic field, which is a bad idea anyway, the quartz watches are tiny little quartz tuning forks. They're tiny. I will show you one. And because they're made of quartz, they have tremendous accuracy. In part, making them out of quartz has a whole bunch of good advantages. Let's see if I can get this guy up here. It'll probably show up initially as a little flea speck. There it is. Okay. Let you get you centered. Okay, now you're zooming in. On the left are the electrical wires. This guy was in a can. Oh, get the focus going here. You can do better than that. Focus. Yeah, good job on the autofocus there. Oh, yay! When I took it out of the can, it's nice shiny silver. It was literally silver. This is the can that it lived in before. Up here. So here's the fork. Bottom tine, top tine, slice coming through there. and there's shiny metal pieces on it. It's actually a complicated metal structure. You know, it leaves something to be desired in the photography here. Why quartz? Quartz is very hard. This is quartz. This is crystalline quartz, so it's the same quartz that you see as crystals out in the field with facets in them and everything like that. Crystalline quartz is very hard, and so when you cut a little tiny fork out of this and you were to smack it, it vibrates many times without losing much energy. It's so it's like a good wine glass. When you tap a good wine glass, it rings. You hear this boing, and it goes on for a little while, as opposed to hitting a cheap glass where you go thunk, you hit thump, it vibrates a couple times and then stops. This guy can vibrate thousands, hundreds of thousands of times without losing much energy, so that only the tiniest little pushes are necessary to keep it going. So how do you push it to get it going? They push it electrically. Quartz itself, crystalline quartz, is what's known as a piezoelectric material. And all that means is that its mechanical behavior and its electrical behavior are coupled to one another. You muck with it mechanically, you get electrical effects. You muck with it electrically, you get mechanical effects. You are aware of these kinds of things in a bunch of contexts. The spark starters for gas grills or for stoves, you hear a little a smack sound, and a spark jumps. Where did that come from? That was a piezoelectric material. A mechanical impact on it caused an electrical effect. And so bug it mechanically and you get electrical effects. Spark. You're also aware of bug it electrically and get mechanical effects. A lot of the speaker systems in your cell phones and stuff like that are piezoelectric. They are devices where they use electrical influences to get a crystal vibrating and making sound. So this little tuning fork is driven into motion electrically. They give it a little electric nudge and it starts to shake. And it's shaking. Its size is chosen so that it's just small enough that it vibrates outside the range of human hearing. Nobody can hear it. It's 32,000 cycles per second. If they went slower, if they made a slightly bigger tuning fork, you would begin to hear, some people would be hearing it whistle, which would be annoying, right? If they made it too small, however, it would vibrate so many times they would have to count lots of motions. And the counting process consumes the battery. So they're juggling between not going too slow, and so you'd hear it, and not going too fast, so it would run the battery down faster. Anyway, they get it moving electrically, and then they watch the motion electrically, because that mechanical motion back and forth creates an electrical influence. And so they could see it vibrate electrically. And so that's how the clock works, is watching these guys vibrate. And quartz itself is almost insensitive to temperature, which is good. Temperature affects some of these other harmonic oscillators. For example, the pendulum gets longer when it gets hotter because things expand with temperature. So it runs slower on a hot day than it does on a cold day. My pendulum does that. It's uncompensated. When it gets hotter, the pendulum gets longer, the period gets longer, the clock runs slow. Better pendulum clocks compensate for this. They use multiple materials so that the pendulum's length doesn't change with temperature. Parts of it expand, parts of it expand more than others. It undoes all the problems and maintains a constant effective length. Quartz, you don't have to compensate much because it almost changes so little with temperature that it keeps good time, hot or cold, within reason. The fact that it's on your wrist helps because then you personally temperature regulate it. All right, with that, have a great break, and I'll see you on Monday after Thanksgiving.